Hi everybody, I'm Harry Shuaib. I'm a founder and CEO of Newton's Tree, and by background a medical physicist in the National Health Service, hence the accent. So I'm going to talk really at the far applied end of the spectrum. So my background is as a medical physicist in a hospital. I built and led the NHS's first AI team, and sort of my day job has always been around how do I adopt AI technology to make patient impact, and that's what Newton's Tree does now as a business as well. So the study is really about how do we do routine clinical risk management of deployed AI technologies, particularly in the diagnostic space. One of the challenges that we have is that a lot of the testing and validation that is done during the sort of adoption phase is all around sort of pre-deployment performance testing, which is important, but actually a lot of the variation and the risk manifests itself post-deployment, right? When the environment changes and the assumptions that you thought were true are no longer true. And that dynamism in the clinical environment makes risk management of these technologies post-deployment really challenging. There's other things that complicate it. So there's often a lack of clarity around whose job it is. Like I talk to a lot of health systems, including our own inside the National Health Service, around, who's keeping an eye on these AI algorithms that you have running? And they're like, oh, the vendor has. And I'm like, the vendor is not keeping an eye on what's happening in your hospital. That's your job. It's your hospital. And the FDA has recognized this and has started talking about total product lifecycle approach. And almost the hospital is becoming a data science lab, which is a really interesting concept. And so what's done today, right? So people do, like the good health systems do audits, right? But it's a really low bar, but some of them don't even meet that. The problem with sort of these ad hoc retrospective audits is that if the sampling frequency is not right, you're going to miss the effect, right? If you're doing it every year, but you've got a whole load of misdiagnoses happening until the next audit date, there's a lot of patient harm potentially happening without anybody knowing. In all domains, relying on user feedback and user-reported incidents is a really weak method of risk management, as we all know. And really, people will often only report something if it's egregiously wrong. The challenge with AI algorithms is that you can have a lot of very subtle mistakes that no one notices, particularly, say, in a diagnostic workflow where you have like subtle overdiagnosis happening, and because radiologists sort of work in isolation, they don't realize until they have like an annual meeting like this, and they're like, oh, have you noticed there's a lot of pneumonia from the AI algorithm? And they're like, yeah, I've noticed that too. And you realize it's been over-reporting pneumonia for the entire year. And ultimately, we don't really have any systematic or scalable way of monitoring AI applications. And that's what FAMOS attempts to solve. So what we did was we did a sort of a feasibility and effectiveness study around whether we could monitor third-party chest X-ray AI applications in real time in multiple healthcare settings. And so the idea is that it's agnostic to who built the product or even what the product does. But can the hospital have a system that can help in risk management? So it was an in silico observational study, so we sort of simulated the clinical workflow. We're now moving this into a prospective setting, but that work hasn't been done yet. And it was done at two large tertiary NHS hospitals. So Greater Glasgow and Clyde is the largest health system in Europe. It covers a third of Scotland's population. Leeds Teaching Hospital is the largest cancer hub in all of Europe as well. So very big centers. And we use two very popular AI applications. Annalise is an Australian AI company that builds a chest X-ray application, amongst other things. And Cure AI is an Indian AI company with a very similar product. Because we also wanted it to be agnostic of the underlying technology as well. So agnostic of the care setting and of the application. And in terms of the data that we used, we asked each respective hospital group to curate a retrospective de-identified adult chest X-ray data set. But we asked them to give us decent diversity along the vectors or dimensions that we thought would be relevant to poor performance of AI algorithms. So we wanted enough people under 60 as over 60. We wanted in winter and outside of winter for different disease presentations, inpatients and outpatients, men and women, as well as presence of imaging artifact and absence of imaging artifact. And we had some exclusion criteria. We had to have the associated radiology report. The other thing that was important is we recruited readers, because one of the important aspects around risk management of AI when it's deployed is automation bias. It's sort of like the dirty secret that no one likes to admit, is that when these things work really well, people stop paying attention. And actually, that's when the most harm comes around. And so we asked each site to also volunteer readers that we would be monitoring who were naive to what we were doing. They thought they were evaluating AI algorithms. We were actually evaluating them. And so we had this sort of simulated monitoring pipeline where we basically ran each algorithm through a metrics pipeline where we would measure things like data quality and AI predictions, and then through a reader pipeline as well, where we would look at how often do the readers agree with the AI and disagree, and does that change depending on what kind of case it is, what time of day it is, etc. And so this is sort of roughly what the workflow looked like. We basically created a PACS-like system. So the readers would log in, they would have a work list on the left-hand side, they would have the original X-ray and then the AI-generated result. And all they would have to say is whether they agree with the AI or if they disagree. And what we also knew was that automation bias doesn't happen straight away, and it's not a point-in-time thing. It's a type of behavior that develops over time. And so we strung out this exercise over 3 months. And so we asked them to log in every Monday, roughly, and to review a few cases. I think it was 18 cases over 10 time points. Because what we expected to see was there wouldn't be any automation bias at the beginning, but as people got lazy, it would creep in. So this is roughly the number of studies that we processed at each site. From a sort of a feasibility perspective, we were able to return monitoring statistics within 20 seconds of the X-ray landing on our platform. So you sort of tick the real-time criteria. I'll skip over this, but this is just the breakdown of the data. This is where the output ended up landing. And this is a lot of dummy data, but I'm going to show you in the next slide the real data. There were 3 key domains that we were really interested in from a safety perspective. So what we did was we said, look, what are the sources of patient harm from using diagnostic AI in this sort of pathway? And really it boils down to basically 2 scenarios, overdiagnosis and underdiagnosis. And then we said, well, what could lead to that? What could lead to overdiagnosis? So one of them I mentioned is automation bias, right? If the AI predicts something wrong and the radiologist is not paying attention, then that automation bias has now led to that harm. The other one is a shift in AI prediction behavior. If there is an update to the AI algorithm and now it's sort of overcalling pneumonia in the middle of summer, you're like, there's probably something gone wrong here. And so we should measure how often it's predicting different things and to see if that matches with the natural prevalence of those things. And the final thing on the left-hand side is data quality. So what we did was we developed an unsupervised algorithm which would look at every piece of data that would come. Before it would go to the algorithm, we would say, hey, is there anything atypical about this data? Because we know if the data is atypical, the prediction is probably going to be unreliable or less reliable. And so this is some of the real data. So this is data, obviously, on the left-hand side from Glasgow and on the right-hand side from Leeds. So this cluster analysis basically is to help you identify outlier data. So things that are clumped together are similar and things that are far apart are different. And what's obvious is that there's a different clustering behavior in Leeds versus Glasgow. In Leeds, you have this one concentric lump. In Glasgow, you have these 4 vertical stripes, which we were very curious about. And so after the fact, we asked Glasgow, like, why, and we looked at all the metadata. It wasn't really obvious to us. So we asked Glasgow, like, why do they think we're seeing this kind of pattern of behavior? And it was because they were actually sending us data from 4 different hospital sites. And each one of those verticals corresponds to a different geographic location. So unbeknownst to us, we were able to detect where the X-rays were coming from. Whereas in Leeds, we were getting it all actually from one site. We also then, particularly for the Leeds data, for the outliers that we detected, we then asked the local radiologist to visually inspect every one of those outliers. And out of the 66 outliers identified, 90% of them were true outliers. And there was all sorts of things wrong with the image, and you can see some of the counts of the reasons. So the most popular reason why we thought there was something wrong with the image was because the patient positioning was wrong. So either they were sitting, or there was some kind of rotation in the patient, or they hadn't inspired correctly, so the positioning of the lungs was incorrect. Then there was anatomical variation, so some people were post-surgery. That would also trip up an algorithm. And then we would also be able to detect implants, so patients with pacemakers and even jewelry. So if you've forgotten, the radiology tech has forgotten to tell the patient to take off a necklace, patient gets imaged with a necklace, the algorithm then trips up. What was really interesting, though, was the human behavior. And so what you're seeing here is the rate of agreement between the human and the AI over those 10 time points that I mentioned that was sort of spread out over roughly 3 months. And you're seeing it averaged across the two centers, Leeds and Glasgow. And so what you can see is that on sort of time point 0, they roughly agree with the AI algorithms the same amount. It's about 70%, which if you take into account the absolute performance of the AI technology and the accuracy of a radiologist, it kind of makes sense. At Leeds, whilst it fluctuates over those 3 months, there's no statistically significant change. By the end of time point 10, they're still agreeing about 70% of the time with the algorithm. Glasgow, on the other hand, almost week by week, there's an increase. And at some points, they are agreeing 15% more with those same AI products than the English site at Leeds, which was fascinating to us. I mean, it was really I was really happy because I was like, eureka, we've seen it. The thing that we hypothesized, we've detected it. But then we said, why did we not see it at the English site, but we saw it at the Scottish site? So not only were the readers naive to what we were doing, we were actually blind to who the readers were. So we asked each site, like, who are these readers? And tell us more about them. So at Leeds, 3 out of the 4 readers that we were monitoring were actually not radiologists. They were what we call reporting radiographers, so radiology techs that do independent reporting. And they had on average 10 years of experience doing independent chest X-ray reporting, and they were doing it 9 to 5, sort of in the working day on sort of time-boxed sessions, so not distracted. The majority of the Glasgow readers, though, were all first and second year residents who only had 1 or 2 years experience reading X-rays independently. And they were doing it at all times of the day. The times where we saw the most automation bias was overnight and at the end of on-call shift. So you have sort of the classic ingredient of less expertise, time poor and distracted, and eureka, you see automation bias. And why this is a really interesting result, particularly for like a national socialized system like the NHS, is if you're making decisions about commissioning a technology nationally, if you test or do a clinical trial at, say, a center like Leeds, and you're like, oh, great, it's working great, the performance is really stable, the concordance with the clinicians is really stable, let's commission it nationally. But that model is not going to hold true because skill mix is different, patient mix is different, data quality is different. We also looked at it to see if there was a difference between the apps, and there wasn't. That same upward trend existed whether the readers were reading Annalise results or Cure results. So it didn't look like there was an obvious connect with any of the applications, and the applications roughly had a very similar accuracy, Annalise being slightly more accurate. We're still doing some of the remaining analysis because what we want to see is, particularly with some of the data quality issues, did that lead to any incorrect answers by the AI, and did that also then lead to misleading radiologists? We know from other literature that does happen, that when the AI is wrong, radiologist performance goes down, but we just want to validate it as part of our study as well. So just in summary, and to give you a chance for some question and answers, we were able to demonstrate that doing real-time monitoring of third-party AI is possible in live hospital settings in a federated way, right? So the really cool thing is that dashboard that I showed you, we can log in through the internet. But none of the data is coming to us, only the metrics are coming to us. So the data is still local, so there's no data privacy issues. But us as a responsible party can observe what's happening locally. And like I mentioned, the input data issues seem to be related to image quality factors, and the automation bias issues seem to be correlated with years of experience and the workload that the person is currently under. Obviously, lots of limitations to this kind of study. It was retrospective in nature. It was a simulated setting. But like I said, we are currently doing it live at both sites. And so maybe next time I can show you how it works in real life. And we had a relatively small sample size and reader group as well, with only 4 readers at each site. And we didn't stratify by case difficulty. I imagine there's a dynamic between like easy cases, like if someone's got like a trauma, where it's like, oh, well, there's obviously something wrong here, versus something more subtle. I imagine automation bias might be different. Yeah, and just want to acknowledge everyone that took part in the study. It took a small army funded by Innovate UK, which is the government sort of innovation funding arm. The other work that we're doing in relation to this is applying the same principles to ambient voice technologies, which is now the latest craze, which is like, how do we make sure that ambient voice technologies are safe and effective as well, and because they suffer from the same data quality issues and also automation bias. But thank you so much for listening.
Questions? Yes.
Thank you. That was very interesting. The question I have is this going to be a one-off effort, or do all AI tools that are implemented in any given hospital, do they need to be tracked over a period of time? Because even if they don't have a bias to begin with, they could develop a bias. And second, I do have a comment. In one of the slides you showed age group is 101 and 102. Is it even real? Wow.
Yeah, that was the max age for a patient. Yes, yeah. So that was showing the range of ages we had. Yeah. Yes, yeah, yeah. Yeah, don't people live over 100 in the US? No. Should monitoring be applied to like everything or all AI? Yeah, of course. Like in any industry, particularly one as high risk as healthcare, every process should be quality managed, right? So how do you know and we do this with with traditional clinical governance, whether you're doing radiation oncology, MD Anderson, or diagnostic radiology, or whatever you're doing audits, right? And performance reviews, and be like, hey, are we actually doing safe and effective care? Just because it's a computer that's contributing to it doesn't mean that's not subject to the same quality management. And so the question comes back, which is, how do you quality manage a service that has a significant AI component? And at the moment, like I said, people just sort of relegate it to like the vendor. Like as if like, you have a Siemens MRI scanner or like a Varian radiation linac. Oh, well, they do the maintenance in the QA. Yeah, but you're the one who's zapping your patients. So you should have some kind of verification or validation process as part of your service. If it was like completely operational technology, so if you're using AI to, I don't know, schedule appointments and things like that, you might consider that low risk enough to be out of scope. But I would say if you're using any sort of clinical or AI technology that touches a patient pathway and you're not doing some kind of frequent monitoring or audit, it's a significant clinical risk.